Hello, you're welcome to New Focus Approach to Mathematics, Basic 9. This is the revised edition, and in this video, you want to learn vectors and want to specifically work on polar vectors in your book. So, we want to talk about polar vectors, but before we do that, let's do a recap on what vector is all about and how we can represent vectors using diagrams. Now, when we talk of vectors, we know it's all about giving directions, okay, magnitude and direction. And so if I have a point A and a point B, and I want to move from point A to point B, you see the arrow, direction of the arrow. It means I'm at point A being the initial and point B being the terminal. So what vector will link A to B? We'll call that vector AB. Vector AB like this. So now we can know the vector AB because the A is the origin. So we move, always in vectors, we move x-axis before we move y-axis. And when you move this direction, we say it's positive. If you go opposite, we say it's negative, because that is the x-axis. If I move upwards, that is positive. If I move downwards, that is negative. Right? Good. So from point A to point B, we are going to move 1, 2, 2. Then we move upwards 1, 2, 3. And so vector AB will be equal to x2 and then x2, then the y3, positive 3. So we have 1, 2, then 1, 2, 3. Okay, now let's see the vector that will link M to N. M to N, that is vector MN. MN, that means starting from M to N. That one we didn't move on the x-axis. There is no movement on the x-axis. So on the x-axis we have 0. Then we move 1, 2, 3, 4 on the y-axis. So we'll say 0, 4. Or let's write it here. MN is 0, 4. Now let's see the next vector. So let's have vector UV, vector UV. And UV, we are moving x-axis 1, 2, 3, 4. But we don't move anywhere to y-axis, and so UV becomes negative 4. Then we say we move 1, 2, 3, 4. So negative 4, then y is 0 because there is no movement on the y part. Then let's try for vector QP. Vector Q, starting from Q, then we head towards P. QP. So QP. And QP, what will be the vector? Because we are starting from Q and we are going to P, we move in the x-axis opposite direction this way. So we are going to move 1, 2, 3, 4, 5, 6, 7, 8. 8. Then so that will be 8, negative 8. Then downwards 1, 2, 3, 4, 5. So negative 5 as well. So the vector QP becomes negative 8, negative 5. Right. Now let's try the last one and see. The last one is KL. KL. Vector KL. Now KL, to start from K and move to L, that means we need to move x-axis 1, 2, 3. Okay, so that is positive 3. And then y-axis we move 1, 2, 3, 4, 5. And that is negative 5. So the vector KL will be 3, negative 5. Good. Now, so that is how we represent vectors using diagrams. Now, let's concentrate on two vectors that are parallel. When two vectors are parallel, one, we say they move in the same direction without meeting each other. Okay, so vector AB and vector CD. Now, let's see vector AB. What is vector AB from the diagram? Of course, A to B, so we have 1, 2, 3, 4. So 4 positive and then up 1, 2. So 2 there. What it means here is that vector AB is 4, 2. Now let's look at vector CD. Vector CD is 1, 2, 3, 4, 5, 6, 7, 8. So CD the x component is 8 and the y component 1, 2, 3, 4. So positive 4 because we went upwards. Now, what is the relationship between vector AB and vector CD? Okay, let's see the relationship. You can observe that if I multiply vector AB by 2, I will get vector CD, which means that the scalar multiplication of AB gives you CD. Anytime you can multiply a vector by a particular number to get the other vector, then we say the two vectors are parallel. So diagrammatically, we can see they are parallel because they move in the same direction. But algebraically, we can only see their parallelity if we multiply one with a scalar to get the other. Good. Now let's take another example under this. Look at this one too. Here we have vector PQ and vector AB. Let's see whether they are parallel. Diagrammatically, you can see they are parallel. But algebraically, can we still see they are parallel? Let's figure out the vector PQ. Vector PQ is 1, 2, then 1, 2. So that gives us 2, 2. Okay, that is positive 2, and then positive 2 for the y side too. Then let's see vector AB. Vector AB. Starting from here, we have 1, 2, 3, 4. And then we have 1, 2, 3, 4. And that gives us 4, 4. So we can see that if I multiply 2 by PQ, I will get AB, which means the scalar multiplication of vector PQ gives us vector AB. That means algebraically too, it's a proof that the two vectors are parallel. Good, they are parallel. Now let's use this idea to solve a question like this. Given the vector AB, this, and vector B, PQ, that, if we say they are parallel, find the value of M. This and this are parallel. If they are parallel, then it means that either AB is a scalar multiply to get PQ, or the other way around. Another way of defining two vectors to be parallel can also be like this. Let's go back to these two vectors. Let me go back to this. Look at these two vectors. We say they are parallel. If you pick the s component 4 is to 8, it should be the same as 2 is to 4. Because they are parallel, the ratio of the s component should be the same as the ratio of the y component. What it means again is that we have 4 divided by 8 should be the same as 2 divided by 4. And here we can see that gives us half. Okay, so when I go the other way around, it will be scalar multiplication of half. And then if I go making the AB fair, then to be scalar multiplication of 2. So if you have this idea, then we can solve this question by saying that since they are parallel, 12 is to 4 should be the same as M is to 3. And no ratio means division, so I can say 12 over 4 should be the same as M divided by 3. If I do cross multiplication, I have 4M is equals to 12 times 3. If I divide both sides by 4, then I have 12 times 3 divided by 4. What is M then? Now 4 can divide itself 1 and divide here 3. So 3 times 3 will give us 9, which means M is equals to 9. Right. I'm sure this example and the previous explanation given will really inspire you to go ahead and solve more questions under parallelity of vectors. Thanks so much for watching.